Well, howdy geometry. Time for another little video from Miss Waite telling you how to do something a little bit new. We don't have a warm-up today, so if you wouldn't mind grabbing that notebook, updating it, writing your questions, writing a summary, and getting a new note page ready. Pause the video and get that business done. All right, so I hope you're buying into that note-taking process. It sure can be helpful. Keeping track of all the things that we're talking about so that you can look back on them in an organized fashion is going to make it so that you are automatically more successful in this class without doing any more homework. It can really make a big difference. So your new notes are going to start with the topic, reflection rules, and glide reflections. Right underneath that, you've got your essential question: what are the rules for reflecting a figure in a coordinate plane? That's what the essential question we're gonna answer today. And then go back to your table of contents and add this topic, reflection rules and glide reflections, and whatever page number you're on so that you can find this stuff later. All right, so I'm gonna start not kind of telling you what to put in your notes. I think you should put, whenever I'm writing, you should put it in your notes. If I've got graph paper up here, it's worth it to grab yourself a little piece of graph paper and create these graphs with me, and then cut your graphs out and glue them or staple them into your notes so that when you see these examples, you can refer to them, because they can be really important when we get a little bit further on and you've had 67 things to remember. You can review this stuff. So this is a bit of a review from our last bit of notes, and so there's probably not a true need to take notes on this, but I wanted to remind you of a couple of things. First of all, we've seen this graph before, the graph of FG. So I'm going to go ahead and get it on this graph here. And -1, 2 is right here, and this is where F lives. And then 1, 2 is here, and this is where G lives. We're talking about reflections. And when you reflect over a line. The line is called a line of reflection. And it required remembering just a little bit of algebra so that we could recognize that this, x equals 4, and also this, y equals x, are equations of lines. And when you go to reflect, you have to put your line of reflection on your graph. And so x equals 4, which is where we're starting with part A, would be a matter of putting a vertical line at x equals 4. Well, here is where x equals 2, and here's where, 1, 2, 3, 4. Every single point on this line right here is where x always equals 4. Y is constantly changing, but x is 4, and that's the line we're going to reflect over. Now, when lines are vertical or horizontal, we have these predictable, countable spaces that we can just count to these lines. And so we can reflect F and G just by counting to the line. So let's take F, and we count 1, 2, 3, 4, 5 spaces to that line. 1, 2, 3, 4, 5 over, and we get F prime. Remember, we call it F prime because we want to be able to tell the difference between F and the reflected image of F, F prime. Now, G is 1, 2, 3 spaces away from the line, and so 1, 2, 3 over the other side gives us G prime, and there is a successfully flipped FG. We flipped it over the line x equals 4. Not a problem. Because we have those predictable spaces, we can count. Well, here's where things run into trouble. When we look at the line y equals x, which is a line where every coordinate point has the exact same value, so things like 0, 0, 1, 1, 2, 2, 3, 3, -1, -1, -2, -2, that's a line. But this line has a slope, and so we cannot count to it. And the reason why is because what does it even mean to count from G to this line? Do we count to this point, to this one, to that one, to that one, to this one, to this one? It's really hard to know because there isn't a predictable space between G and that line. Same thing with F. So we need to have something better. And it turns out we do. And that's what we're talking about today. Coordinate rules. Now, coordinate rules are like all other rules for transformations. They have this x, y, and then an arrow, but then notice the difference. They don't have any numbers in them, and that's because they're telling you what to do with the points. So if you're going to reflect in the x-axis, you're going to take every point and you're going to turn the y to its opposite value. If it was positive, it'll be negative. If it was negative, it'll be positive. If you're going to reflect in the y-axis, you're going to take each point and you're going to turn the x to its opposite. And those are nice rules, but you don't need them all the time because oftentimes you can just count to the x and the y-axis since they're vertical and horizontal. Here's where the really good stuff starts. In order to reflect in y equals x, which we could not do by counting, now we have a rule. And this rule just says take every point and just switch the values around. X becomes y and y becomes x. And then if you want to go the other way, there's a great line called y equals negative x, which I'll show you in a bit. Then you flip the values and they turn to their opposite. So let's look at FG again. This is the same points that we had before. F is at -1, 2, and G is at 1, 2. And now we're going to find the coordinates of the endpoints of the image after a reflection in the line y equals x. That's exactly what we were trying to do here. But we couldn't. But now we have a rule, and so we can. So because we're reflecting in the line y equals x, we're going to use this rule right here, and we're going to take our points, and we're just going to run them through that rule. So F lives at -1, 2, and we're going to run it through the rule, and the rule just says take each point and flip them. So F prime will live at 2, -1. And that's all there is to it. We know where F prime lives now. And now we can do the same thing with G. G, looks like a 6. G lives at 1, 2. And so to run it through the rule to get G prime, we just flip those values. 2, 1. It's magical. Now let's plot those points back on this graph and see if we're right. So F prime lives at 2, -1. I'm just going to write that down. F prime lives at 2, -1. And then G prime lived at 2, 1, correct? Let's plot those and see if it looks like the reflected version. So F prime lives at 2, -1. Right here is F prime. And then G prime lives at 2, +1, which is right here, G prime. And gosh darn if that doesn't look like a great reflection over that line. That's how you do these. If your lines are vertical or horizontal, you can pretty much reliably count. But if your line has any slope whatsoever, you're going to need a rule. And we have a rule for y equals x and y equals -x. There are other rules, but we're not going to study them. These are the ones that you need. Okay? So let's kind of push this idea just a little bit. Sometimes you have to be careful about what you're being asked so that you don't do too much work. Just putting that out there. So let's look at this problem. Triangle JKL has vertex coordinates of those. What will the coordinates of JKL prime be after a reflection in the x-axis? So because we're talking about the x-axis, our first instinct might be to go ahead and count. But notice that you're being asked for coordinates. You're not being asked for the graph. You could make a graph and then pull those coordinates off. Let's do that. So let's have JKL. Well, it's at 5, 3, 1, 2, 3, 4, 5, 1, 2, 3, right here. Here's J. K is at 1, -1, 2, here. Here's K. And then -3, 1, 2, 3, +1, 2, 3, 4 gives us L. And here's our triangle. Okay, that's step 1. Now step 2 is to count to the x-axis because that's what we are reflecting over. So we can do that. Let's see, L lives at 1, 2, 3, 4 away from the x, so 1, 2, 3, 4 out the other side is L prime. K is 1, 2, 1, 2, so here's K prime. And J is 1, 2, 3 to the x-axis, 1, 2, 3 out the other side for J prime. And now we have our new reflected triangle, and it looks really good. Okay, great. So we've got this great graph, but it's not what we've been asked. We've been asked for the coordinates. So we have to pick up and figure out what these coordinates are. And so L, we can just count it. Oh, let's start with J, just to keep the order. J is at 1, 2, 3, 4, 5, negative 1, 2, 3, 5, negative 3. Okay, we've got 1. Now we need K. Let's see, K lives at 1, 2. And then we've got L prime that lives at negative 1, 2, 3, negative 1, 2, 3, 4. Negative 3, negative 4. And we have finally answered this question. So that's one way you could go. You could graph the triangle. You could count to the x-axis because it's horizontal. Counting is totally open to you. And then you can grab those coordinates and write them down because you were asked for the coordinates. That's a way you can go. But you want to know an easier way? Use the rule. Because the reflection in the x-axis rule can be really handy when you're just asked for coordinates. When you don't really need the graph, all you have to do is run those coordinates through the rule. Well, if J lives at 5, 3, doesn't the rule tell us that J lives at 5, negative 3? If K lives at 1, negative 2, then the rule would tell us that we have 1, positive 2. The negative sign on that y just turns it to its opposite. And then L, which lives at negative 3, 4, I forgot a negative sign. Oops. Actually lives at negative 3, negative 4, which, yeah. So the point here is that there's a couple of ways you can go, and it depends on what you're being asked. What this question wanted was the coordinates of that triangle. You could grab graph paper, slap that triangle down on the graph paper, count the distance to the x-axis, plot that new triangle, and then pull its coordinates off. You could do that, and that's fine. But it would be easier if you get comfortable with the rule. You have a rule for the x-axis. Why not use it? Here's another type of problem. Now this says that they want the graph. And so you're going to need to use graph paper for this. And very handily, the polygon is already on that graph. And what we're being asked is a reflection in the line y equals negative x. And so let's go ahead and work through this problem. So the first thing is to recognize what that line looks like. Now y equals x is the line where all the coordinate points have the same value, but y equals negative x is where they have opposite values. So 0, 0 is on that line, but so is 1, negative 1, and 2, negative 2, and 3, negative 3, and then there's negative 1, 1, negative 2, 2, negative 3, 3, and so here is that line. This is what y equals negative x looks like. It's the exact opposite of y equals x. Now, because it has a slope, we cannot count. So there's no counting to be done in this problem. We're going to have to use a rule. And so, why my little arrows aren't here, I don't know. There's supposed to be arrows on all of these. Notice that we have a rule for y equals negative x. Here it is. And it says just take each one of those points and flip the values to their opposite. flip the values, and then turn them to their opposite. So we need the coordinates. And if we don't have the coordinates, we can't use the rule. And so let's go ahead and do that. Now let's call this A, B, C, and D, and then let's get some coordinates. So A lives at, and this isn't very well drawn, so let's just, do that. A lives at negative 1, 2, 3, 4, positive 1, 2, 3. So A lives at negative 4, 3. Let me count that again. 1, 2, 3, 4, 1, 2, 3. Yeah. B lives at 1, 2, 3, 4, 5. 1, 5. C lives at 1, 2, 3, 4, 1, 2. Yeah, I just need to check it again. D lives at, let's see, 0, negative 1, 2, 3. All right, so now that we have those coordinates, we can run them through the rule and then graph them to get the graph. This is the kind of problem that takes a little bit of work because you need the graph and the rule since you have a sloped line. All right, so let's start with A. A, that lives at negative 4, 3, is going to become A prime after we run it through the rule. Well, we need to flip those values and then turn them to their opposite. And so negative 4, 3 becomes negative 3, positive 4. The 3 turns negative and goes to the x spot, and the y turns positive, the 4 turns positive and goes to the y spot. Flip them, and then also flip their values. Let's look at B. B started out at 1, 5, and so B prime, after using the rule, will be what? Negative 5, negative 1. You got it. All right, here's C. It lives at 4, 2. To get C prime, we're going to have to flip them twice. Flip them, the values, and then also flip their position. And so you have negative 2, negative 4. And the last one, D, lives at 0, negative 3. And so to get D prime, we have to flip them. And so we have positive 3 and then 0, because the opposite of 0 is 0. And now we can plot those points and see what we got. So A prime is at negative 3, 4. Here's negative 1, 2, 3, positive 1, 2, 3, 4. Here is A prime. And then B prime is at negative 5, 1, 2, 3, 4, 5. Negative 1 here. Here's B prime. And then C prime is at negative 2, negative 1, 2, 3, 4. Here's C prime. And D is at positive 3, 1, 2, 3, 0. Here's D prime. And then you connect them, and it looks like a mess. But there's your reflected figure. It flips right on top of that line because the original figure is on top of the line too, so it'll flip on top of itself. So it kind of depends on what you're being asked, whether or not a rule comes in handy. Here, a rule would have been a time saver because we were asked for the coordinates, and even though you can graph and count to the x-axis, running it through the rule was just kind of quicker. On this problem here, we needed the graph, and so we had to use both graphing and the rule. So what you're doing is paying attention to what you're being asked and what you have to do to get your answer. So let's change the subject slightly because we're going to talk about combining again. Remember how we talked about combining translations into compositions, where you translated and then you translated again, and now you had a composition? Well, there is one type of specific composition that has a predictable name, and the name is called a glide reflection. Anytime you combine a translation, look at how we have PQ in position 1, and then it translates to position 2 to get PQ prime, and then you add in a reflection over a line, see position 3 there for the green segment, that is called a glide reflection. So the definition of glide reflection is the composition of a translation and a reflection. Every time you translate and reflect at the same time, one or the other, one and then the other, anytime you combine those two things, a translation and a reflection, it has a special name called a glide reflection. So let's do one. Now you're going to be using all of your rules here, and so I have them, and then you also have some graph paper, and here is your glide reflection. You have this translation, which you're going to do first, and then your reflection, which is going to be second, and you will have a glide reflection on your graph paper. So we have triangle ABC with vertices A, B, and C, and then we're going to glide reflect it. And so A starts at 3, 2, right here, A. B starts at 6, 3. Let's see, 3, 4, 5, 6, 1, 2, 3, right here, B. And then C is at 7, 1. Ooh, that's getting close to the edge of the paper. 2, 3, 4, 5, 6, 7, 1, right here. Oh, I hope we have enough room. This will be fun. Okay, there is our pre-image before the glide reflection. So the first step of this glide reflection is the translation, and we have a rule where we're going to take X and move it 5 units to the left, and Y doesn't change at all. It doesn't go anywhere up or down. And so A, to get to A prime, has to go 5 units to the left. 1, 2, 3, 4, 5, and we have A prime. B has to go 5 units to the left. 1, 2, 3, 4, 5 for B prime. That Y sitting there with no adding or subtracting is just telling us that it doesn't go anywhere up or down. And then C goes 1, 2, 3, 4, 5 to get C prime, and we have translated our triangle. Now we're going to reflect our triangle. And remember, we're reflecting the prime triangle. We're doing first the translation, and then we reflect that triangle. So we're reflecting in the x-axis. So think about this. Do you need the rule? Are you being asked for the coordinates, or are you being asked to graph? You're being asked to graph. So the rule might not even come into play this time. Because it's the x-axis, you can just count. A prime is 1, 2 away from the x-axis, so A double prime is going to be 1, 2 right here. A double prime. B is 1, 2, 1, 2, 3 away from the x, 1, 2, 3 out the other side gives us B double prime, and then C is 1 away from the x, and so 1 out the other side gives us C double prime, and this is a graph of our glide reflection. We translated, and then we reflected. And that is what a glide reflection looks like. All right, y'all. That is about enough of that, don't you think? Our topic today is reflection rules and glide reflections. And you have a Big Ideas Math assignment waiting for you. Reflection Rules Plus is what it's called. I didn't have enough room to write out the whole thing, so I just called it Reflection Rules Plus. Can you answer this essential question? What are the rules for reflecting a figure in a coordinate plane? Gosh, I hope so. If you can't, you know to come to office hours, right? You could just sit there and do your homework during office hours with me on the other side, and anytime you have a question, I'm right there. That's totally okay. Or you can pop in, ask a question, and pop back out. Office hours are yours to use as you see fit. I hope whatever you do, it's wonderful and it's good for you. Talk to you later. Bye.